In a previous video lesson for this unit, we used the law of Biot-Savart, which can be stated as dB equals mu naught over 4 pi times I times the cross product of ds and r hat, all divided by r squared. We use that law as a brute force method in order to determine what's the magnetic field at some indicated point if we know the amount of current that's flowing through the wire and we're given the distance between that point and the center of the wire. The result, and you can go back and review that video if you need to, but the result was that B is equal to mu naught I over 2 pi y times cosine theta naught. So if the wire has a finite length, then the distance from the point in question to either end of the wire can be thought of as having some particular angle, theta naught. And if the wire is very long, then that value of theta naught approaches 0 degrees, and the cosine of 0 degrees is equal to 1. So for a very long wire, B is equal to mu naught I over 2 pi y. Okay, well, this video we're going to use an alternative method in order to see if we can derive that exact same equation. The other method is Ampere's law. Ampere's law is one of the 4 equations in Maxwell's equations. So I would encourage you, if you haven't yet, to take a look at my video that introduces Maxwell's equations, and you'll find that Ampere's law looks somewhat like Gauss's law for electricity. Ampere's law is a law for magnetism, and it says if we take the integral of B dot ds, that's equal to mu naught, the permeability of free space, multiplied by the amount of current enclosed by some Amperian loop. So here's how we apply that law to find the magnetic field near a long straight wire. So let's draw that wire one more time. So just like when we did Gauss's law for electric fields, it was important to picture what our Gaussian surface looked like. When we use Ampere's law, it's important that we picture what our Amperian loop looks like. So I'm going to draw an Amperian loop for this wire, and I'm just going to draw it as a circular path, concentric with the center of the wire. Okay, so S equals 2 pi r would be the full perimeter around my Amperian loop, but ds is then just breaking that Amperian loop into little bits, right? ds, so that when I integrate all the way around ds, that gives me 2 pi r. So there it is. I've chosen at liberty some Amperian loop. Well, not completely at liberty, right? I'm trying to match the shape of my Amperian loop to the expected shape of the magnetic field lines. I already have, based on Ørsted's discovery, an inkling that the magnetic field lines, when current flows to the right, form circular loops around the wire. Wait, I'll give you a minute to apply the right-hand rule and see if you can determine which way I should draw these arrowheads on my circular paths. So if all those green circles represent magnetic field, in which way are they pointing? Put your thumb in the direction of the current, curl your fingers around, right? And you agree with me on this one, that the magnetic field lines wrap around and point this way? Or is it the other way? Do they point this way? I think that's the case. Okay, so there is magnetic field along every bit of my Amperian loop, and in fact, gosh, how does this work out? If I pick any one of these little things ds, if I draw my Amperian loop one more time, make it a little bit bigger, then I picture, okay, for that little part of my Amperian loop, is there any magnetic field there? And there is. The magnetic field at this point lies completely parallel to my Amperian loop, meaning the dot product between B and ds, that dot product is maximized. B dot ds should be the same thing as BDS cosine theta, but the angle between B and DS is 0 degrees, which just gives me 1. And so I can simplify from step 1 to step 2 and say it's the total integral of B ds. I can get rid of the vector nature and get rid of the dot product. And that's equal to mu naught times the amount of current enclosed by that Amperian loop. Now here's another thing I notice. I really think I chose my Amperian loop wisely, because if I look at that ds, I believe the magnetic field that exists around that portion of the loop is just as strong as it is for any point along the loop. By making my Amperian loop concentric with the wire, I've guaranteed that the magnetic field has the same magnitude for every ds. So you know what I'm going to do in step 3? I'm going to take the magnetic field out of the integral sign because it really represents a constant in this case. So this is B times the integral of ds is equal to mu naught. Now, how much current is enclosed by my Amperian loop? Well, in this case, all of the current passes within the Amperian loop. So the amount of current enclosed is the current shown. So now we just have to evaluate this integral, but I think we already stated that earlier. If I add up all the way around the path, it just gives me the circumference of my Amperian loop, 2 pi r. So we have B times 2 pi r equals mu naught times I. So this gives us B equals mu naught I over 2 pi r. Now, do you see it? When we use the brute force method, we got B equals mu naught I over 2 pi y. Well, the only difference is just a matter of semantics, right? We chose to call the distance from the middle of the wire a variable we called y, and Shakespeare said it best, a variable by any other name would smell as sweet. So if now I'm choosing to call the distance from the center of the wire something called r, it still ends up really being the same equation, right? And I think you'd agree with me, this approach based off of Ampere's law was not as mathematically involved as the approach we took when we had used the law of Biot-Savart. So the takeaway is there are two methods in general that we can use to determine the magnetic field for different currents. One is a brute force approach based on the law of Biot-Savart. It says a little bit of magnetism can be found by taking mu naught over 4 pi I ds cross r hat over r squared, and then to get the overall magnetic field, I have to integrate all of those little contributions to the magnetic field. The other method is a little more elegant, but it requires some high degree of symmetry, and that method is Ampere's law. And Ampere's law tells us that the product of magnetic field and path around a completely closed loop known as an Amperian loop is dependent entirely on the amount of current that's enclosed by that Amperian loop. All right.